Keeper 6.2, Riemann Sums. All right, so the main question we need to ask ourselves is, what is an integral? Well, the integral is simply the area underneath a curve. So if you have some curve, it's the area from the curve to like the x-axis. It also tells you like how much you have accumulated or how much you've lost from one point to another point. And again, it's just the derivative backwards. All right, so a Riemann sum is a way of approximating an integral. So if you don't know how to actually calculate the integral, we can calculate a Riemann sums to get a good approximation. Now we have a lot of different types of Riemann sums. And so when you're doing Riemann sums, generally you're creating a rectangle or a trapezoid or some shape that you actually know how to find the area of, and then you add all those little areas together. So the first one, or the first two we're going to talk about, is the right and the left Riemann sum. So for the right Riemann sum, we're going to draw rectangles pulling from the right side of each interval. So we're going to break the figure into intervals, and we're going to pull our rectangles from the right side. Whereas in the left Riemann sum, we're going to make a bunch of, again, rectangles, and we're going to pull the area or pull the top of the rectangle from the left-hand side. I know these formulas look a little crazy, but I promise they're not as crazy as they look. All right, so our first example, make sure you have this graph cut out and put into your keeper. We want to approximate the integral using a right endpoint method. And then they told us specifically to use 5 subintervals. Now, every question they have to tell you how many intervals to use so you know how to break up your picture or your function. All right, so using 5 integrals, since I'm going from -1 to 4, each subinterval will be length 1. So I'm just going to draw in on my graph 5 subintervals. All right, and as you can see, I have equally sized spaced out intervals, and I have 1, 2, 3, 4, 5 of them. All right, now because I'm doing a right Riemann sum, if I look at this first interval, this interval is going from here to here. But because I want to do a right Riemann sum, I want to use specifically this one over here because this is the interval to the right. So when I draw my top, I'm going to draw it from the right. Same thing in the next interval. I'm going from this piece to this piece, but I want to use specifically the right one because I'm drawing my interval, I'm doing my intervals from the right because I'm doing a right Riemann sum. So just so you guys get an idea of what I'm doing, I'm pulling my tops, or I'm creating my rectangles from the right. And so I start on the right, and I'm using the right interval. And then I'm going to go to the next one, and I'm going to use the right side of that. And then the next one, use the right side of that, right, and right. And then I just create my rectangles. So I create boxes all the way down. All right, once I have my intervals and my rectangles created, I shade in each rectangle. So, and I typically use 2 different colors just so I can see the different shading, but y'all can shade it in however you want to shade it in. All right, so I shade in each rectangle. And then what I want to do is I actually want to find the area of each rectangle to get an approximation. So for my right Riemann sum approximation, I'm going to take the area of each rectangle. Now, what I need to understand is that area for a rectangle is equal to base times height. All right, and all of these rectangles that we drew have a base of 1 unit. So it was 1 unit, that had a base of 1 unit, this one 1 unit, and so on and so forth. Each rectangle had a base of 1 unit. So I'm going to do 1 times, so for this first rectangle, 1 times 5 because the height of this rectangle is 5. And then I'm going to do 1 times 4 because the height of this rectangle is 4. Now the next green rectangle is going to be 1 times 2 because the height of it is 2. The next blue one is going to be 1 times 2 again. It's the same exact one as the previous. And then the last one is going to be 1 times 7 because it goes all the way up to 7. Now, I could write it out like that, 1 times 5, 1 times 4, and so on. Or I could just say 1 times all of the heights since all of the bases were the same. So I say 1 times 5 plus 4 plus 2 plus 2 plus 7. Then I add all that up, and I get that my area is approximately 20 units. Now, looking at this graph, it appears that a lot of my pieces or big chunks of my graph is over the curve. So looking at this, it appears to be an over approximation. All right, so the next example is same exact graph, but this time we're doing left endpoints, again using 5 subintervals. So I'm going to break it up into my 5 subintervals. And then this time I'm going to pull from the left. So instead of starting on the right and pulling from right to left, I'm going to pull left to right. So I'm going to pick the interval on the left-hand side. So this first one, I'm going to pick this interval because that's the left. All right, the next one, I'm going to pull this interval because that's the left. All right, and I'm going to continue that throughout the whole picture. Now, once I get that, again, I'm going to shade in my rectangles. And then I'm going to approximate it using my Riemann sum. Now, just like before, each base has a length of 1, and the area of a rectangle is base times height. So I have 1, and again, I'm writing in the shorter form. I have 1 for each one of my bases, but my heights of these triangles are going to be 2, 5, 4, 2, and 2. And so I have 1 times 2 plus 5 plus 4 plus 2 plus 2. That approximately equals 15 units. Now looking at this picture, I have a lot of space under the curve that was not covered. So just guessing, I'm assuming that this is probably going to be an underestimate of the true area. The idea is that you want to pick a Riemann sums method that's going to give you the best approximation. And truth be told, the left or the right Riemann sums are good approximations, but you probably want to reduce your base by increasing your subintervals. So the more subintervals you have, the better approximation you'll get. So like instead of doing 5 subintervals, if I had done 20 subintervals or 100 subintervals, my approximation would be a lot closer. All right, so we have 2 more types of Riemann sums. We have our midpoint Riemann sum, which is basically the same as the right and the left, except for instead of pulling from the right or the left, we're going to pull from the middle. And then we have our trapezoid rule, which basically says we're going to take the endpoints of each interval and we're going to connect them, making trapezoids. Again, the formulas look a little crazy, but they're not as bad as they look. All right, so the first one, same graph, we're doing the midpoint method. So I'm getting my 5 subintervals. And then what I'm going to do is I'm going to cut each subinterval in half. So I'm going to put like a little dotted line down the middle of each subinterval. Now, the tops of these rectangles that I'm going to draw are going to touch that middle dotted line that I drew. So I'm going to draw a top here, a top here, a top here, a top here, and a top here. All right, so everywhere where I touch the middle, I'm going to draw my tops. All right, and then I just create my rectangles. Again, just like before, I'm going to shade in each region so I can see my rectangles a little bit better. And then I'm going to figure out my approximation. So for this particular graph, again, all of my bases are 1. They're still rectangles, so we have area equals base times height. And so I have 1 times the first height, which is 4, the second height, which I approximated to be 4.8, the next height is 3, then we have about 1.5, and the last one is 4. Adding all that up, I get 17.3 units. I have some pieces that are outside and some pieces that are inside. It looks like a pretty decent approximation. I'm not really sure, so I'm not going to guess as to whether this one was over or under. Shoot. All right, so next we have the same exact graph. We're approximating the integral this time using the trapezoid method, which is really my favorite method. I feel like it gives you the best approximation. We're doing 5 subintervals again, so I'm breaking it up. It's my 5 intervals. And then for your trapezoid method, you're going to connect your endpoints. So like I'm going to connect this piece to this piece. And then I'm going to connect this piece to this piece, and so on and so forth. So I'm just going to connect all of my tops, and I create trapezoids. Now the catch to really understanding your trapezoid method is that you kind of want to look at it on the side. You almost want to like turn your head sideways so that you can see the trapezoid. All right, now I'm shading in my regions, and again I can see those trapezoidal regions. So to calculate the approximation, I need to understand that again the trapezoid has height 1. So again, if I turn my head or I turn my picture sideways, I realize that this purple area that I'm drawing in, those are my heights of my trapezoids. All right, they're not the base, it's the height of my trapezoid. And so each trapezoid still has height 1. And then, let me use like red. This would be like my base 1, and this would be like my base 2 of the trapezoid for the first green region. So if you remember, the area of a trapezoid is 1/2 height times base 1 plus base 2. So the first one is going to be 1/2 times 1, that's my height of each one. And then this first base is 2, whereas the second base is 5, so 2 plus 5. And then I'm going to do the next blue triangle, so I have 5 as my left base and 4 as my right base. So 5 plus 4. And then I'm going to do 4 plus 2 for the next green, 2 plus 2 for the last blue, and then 2 plus 7 for the last green. Once I write all that out, I can simplify that, or I could write it a little bit better using that formula from the previous screen for your trapezoid rule. So I can, instead of saying 2 plus 5, 5 plus 4, 4 plus 2, so on, I could say 1 times 1, and then 2 plus 2 times 5, plus 2 times 4, plus 2 times 2, plus 2 times 2, plus 2, plus 7. Now realize that I can do 2 times 5 here because I'm using the side length 5 twice. And then I can do 2 times 4 here because I'm using the 4 side length twice. And I'm doing that for each piece except for the endpoint. So except for this first 2 right here and this first 7 right, or this last 7 here, I'm only using those once. But everything in the middle I use twice because I'm using it for 2 trapezoids. And then all I do is simplify it out. I get 17.5 units squared. And again, that's a pretty decent approximation. All right, last 2 Riemann sums. We have the last 2 methods of your circumscribed method, and then you have your inscribed method. Your circumscribed method is you want to pick the highest point in the interval to create your rectangles, whereas your inscribed method, you want to pick the lowest point in the interval to create your rectangles. When you pick your points for the inscribed or the circumscribed, it does not have to be endpoints like, for instance, your right and your left Riemann sum. It could be some value inside of the integral or interval that is your lowest or highest. It doesn't have to actually be the endpoint. All right, so this time I'm going to get a little fancier. I'm going to do 10 subintervals just to show you that when you do more subintervals, you have a more accurate answer. All right, so I'm breaking this thing into 10 subintervals. And again, I want even subintervals. So since I was going from -1 to 4, I had to get an interval every 1/2. All right, so for the circumscribed method, I'm going to pick the highest point in the interval. So when I look at this first interval from -1 to -1/2, the highest point is right here at -1/2. So that's where I'm going to draw my tops. And I'll do this for every single interval. Just pick the highest point and draw my tops to get my rectangles. All right, once I get all my tops, I should realize that every single rectangle is pretty much over the curve because, again, we're doing the circumscribed method. And so I just shaded in. All right, so now to get the approximation, we have to realize that each base now is 1/2 because I increased my subintervals, so that decreased the base. And then since we're dealing with rectangles, again, we have area equals base times height. All right, so I have 1/2 for each one of my bases, and then all of my heights I can add up. So like 4 plus 5 plus 5 plus about 4.8, and I keep adding all those up until I get to the end. From there, I sum it up and divide by 2, and I get an approximation of 20.4. This is clearly an overestimate because every single rectangle that we drew was over our curve. All right, so next we're going to approximate the integral using the inscribed method. Again, we have 10 subintervals, so I'm breaking my thing up into 10 intervals. This time I'm picking the lowest point of the interval. So whatever's lower inside of each interval, I'm picking that point. So for here, this first interval from -1 to -1/2, the lowest point is down here at -1, and so I'm going to draw my box there. And I'm going to do that thing for every single interval. I'll make sure I'm underneath the curve on every single part. and then I shade in my pieces. Now this is, again, I can clearly see this is going to be an underestimate because all of my rectangles are underneath the curve, so I'm missing parts of it. But to get the approximation, again, I have to realize that each base has, or each base is 1/2 because I'm doing 10 subintervals. The area of each rectangle is base times height. So I have 1/2 times all of my heights, which in this case is 2, 4, 4.8, and so on. I add that up and I get an approximation of 14.5 units squared. Again, this has to be an underestimate because we use inside values for every single rectangle that we drew.